In a previous section, we talked about the probability rule for addition, and in addition, we had to look to make sure two events were mutually exclusive or disjoint. Well, in this series of videos, when we talk about the multiplication rule for probability, we want to focus on the multiplication rule when we have independent events. So first we need to define what we mean by independence. Independence has to do with the probability of one event being impacted by the probability of a second event. So for example, if I'm looking at this idea here of my favorite color, if my favorite color is blue, or the probability my favorite color is blue, that doesn't have any impact on me choosing fishing as my favorite hobby. However, if we look over here at the dependent side, you are late for school, your car runs out of gas. So the probability of you being late for school is probably impacted by the probability of you running out of gas, because that would cause you to be late for school. So this idea of independence, when we think about two events that are independent of each other, we are determining whether the occurrence of event 1 or event E has any probability, has an effect on the probability of event F. So that's our idea for independence. Let's look at this concept here, or this idea, this example here. Suppose that we flip a fair coin twice, and we want to know what's the probability that it will land on heads for both flips. So we have the probability of heads and heads. Before I figure out what the probability is, let's see what the sample space for this event would look like. If we flip the coin the first time, we get a head. We flip the coin the second time, we get another head. We flip the coin the first time, we could get a head. Flip it the second time, we could get a tail. Flip the coin the first time, we could get a tail. Flip it again, we get a head. Flip the coin the first time, we get a tail. Flip it the second time, we get a tail. There's 4 possible outcomes for flipping a coin twice. And if we notice, there's only one outcome out of the 4 that resulted in 2 heads. So we would have a 1 in 4 chance, or the probability is 0.25. Now, just like we saw when we were looking at section 5.2 for the addition rule, there's got to be a better way that's maybe less cumbersome for us to be able to determine the probability when we have independent events such as this. Now, one quick note, why are the flipping of coins independent of each other? If I take a coin and I flip it the first time, we know intuitively that the probability is a 1 in 2 chance, or it's a 50-50 chance it lands on heads. If I flip the coin a second time, the probability of landing on heads is not impacted by the probability of flipping it the first time. Each flip is independent of each other. Therefore, we have events occurring in this scenario that are independent of each other. Because of that, we can come up with this rule here. When we have two events that are independent, the probability of E and F, or events E and F, say that we're going to multiply the probability of event E times the probability of event F. Now, let's apply that to the example we were just looking at. First, I want you to notice that for the rule of multiplication, the key word we're identifying here is and. When I see and, I know that I'm going to be multiplying my probabilities together. So if we want to know what is the probability of heads and heads, according to the rule we see here, we're going to take the probability of heads for one flip and multiply it times the probability of heads for the second flip. So the probability of flipping a head is a 1 in 2 chance, and we multiply that by the probability of the second event, which is a 1 in 2 chance again for getting heads. And if you don't remember how to multiply fractions, we're going to multiply numerator to numerator, so 1 times 1 is 1, and then we multiply denominator to denominator, so 2 times 2 is 4. And you can see that by applying our multiplication rule for independence, we get the exact same outcome as we did when we did it using the sample space. So the multiplication rule here, when we have two events that are independent of each other, we will multiply those two probabilities together. And another note I would just tell you about, just in case it's not clear, in the case of our example here, the probability of a head times the probability of that same event again ends up, we're applying the rule in the same fashion whether I have two of the same events or whether I have two different events. So here I have in the rule, I have probability of event E, and then I have what I'm assuming would be a second event, the probability of F. Either way, I'm going to be multiplying probabilities together as long as the events themselves are independent of each other. So let's look at one example together that applies this rule. So here I have the example that has to do with my children. I have 3 children, and as you can see from the picture, all 3 of my children have red hair. So imagine my surprise when every time I had a child, I ended up with a child that had red hair. So by the time I had 3 children who all have red hair, I just thought that was a miracle. So let's see if we can determine what the probability is for me to actually have all 3 children turn out having red hair. Well, before we do that, we need to think about recessive and dominant genes. This kind of takes us back to something that you may have remembered from some sort of biology class before. If we do the Punnett square, I believe it's called, where we talk about dominant and recessive genes for hair color in this case, I, the mom of these kids, am a brown-haired woman whose dad was redhead. So my dad had red hair. My husband, my children's dad, my husband has red hair. So in order for him to have red hair, he has to have 2 of the redheaded genes because red is recessive. Me, because I am brown-haired, I have a brown and a redhead gene because my dad was redheaded. So the possible outcomes for the combinations here look like this. We could have a brown and a red. We could have a brown and a red. We could have a red and a red. And we could have a red and a red. These are the 4 outcomes, the 4 possible combinations, if you will, of the genes that my husband and I would pass on to our children. And again, as long as you have a brown paired with a red, then you're going to end up with a brown-haired kid. As long as I have 2 red genes paired, I have a redheaded kid. So the probability of a red is a 1 in 2 chance because it's 2 out of 4. The question I'm asking is, was it really unusual for me to have all 3 children have red hair? So the probability, all reds. What does that mean in relation to what we're looking at here with this new multiplication rule? Well, think of it as this. In order for me to have all redheads, I would have to have the probability of 1 kid having a redhead and the probability of another kid and the probability of another kid. So all 3 of them, a red and a red and a red. And anytime I'm using the word and, I know that I'm going to be multiplying their probabilities together. So this should look like the probability of 1 redhead is 1/2. The probability of the second child having red hair is 1/2. The probability of the third child having red hair is still 1/2. Multiply numerators together, so 1 times 1 times 1 is 1. Multiply denominators together, that would be 2 times 2, which is 4, times another 2, which is 8. It ended up being that this was a 0.125 or a 12.5% chance for me to have all three of my children having red hair. So would this be unusual? Remember, for something to be unusual, we are going to follow the rule that it needs to happen less than 0.05 times. In other words, less than 5% of the time. It was a 12.5% chance for me to have redheaded children. So it's not considered unusual because 12.5 is greater than 5%. So while it's a small chance, it's not an unusual thing to have happen. And the other thing that I would point out real quickly before we end this video is, were these events independent of each other? Does the chance of one kid having red hair impact the probability of the second or even the third child having red hair? Hopefully you can see that each event, each birth, is going to be independent of any other births that were to happen. So this is an example of applying our new rule, the multiplication rule, when we have two events that are independent of each other.